Look at the surface of Mars today, and you see a frozen, irradiated wasteland. It is a dry desert of dust and rock, stretching for millions of square miles, without a drop of standing water. Despite this barren reality, space agencies are spending billions of dollars on deep space missions to find signs of biological life here. On the surface, the search feels paradoxical. Biology requires a thriving, dynamic ecosystem, and looking for it on a dead, arid crust seems logically impossible. But the evidence isn't missing. It is just obscured by the dust. Finding it requires us to shift our perspective and change the scale at which we look at the planet. The modern surface is a planetary fossil. Reading that history requires a journey from macrogeography in orbit down to microscopic chemistry in the soil. We begin in orbit, using satellite imagery to analyze the massive topographical features of the Martian crust. These images reveal massive, winding scars etched into the surface. These channels aren't random. Tectonic cracking creates jagged, intersecting lines, but these networks merge into a single downward direction, a pattern mirroring the fluid dynamics of Earth's river systems. At this macro scale, these patterns indicate that the Martian landscape was once carved by an active planetary water cycle. To see how that water functioned, we move from orbit down to the surface, using rovers to inspect the geology up close. Along the hillsides, we find distinct stratified rock formations. These layers are the result of sedimentation. They are created when particles settle out of standing water and are stacked chronologically, one on top of the other, over thousands of years. Looking closer at fragments on the ground, we find rounded pebbles mixed into the dirt. While wind erosion creates sharp edges, these stones are uniformly smooth. To achieve this shape, they tumbled against one another in a moving water current. These geological anomalies indicate that this terrain isn't just a desert, it is a dynamic, ancient riverbed. To find evidence of the water itself, we have to look past the physical shapes of the rocks and examine their chemical makeup. When the rovers analyze the soil, they find these uniquely hydrated minerals embedded deep within the Martian sediment. These minerals cannot form through heat or pressure alone. Their molecular structure requires liquid water to bind and crystallize. This microscopic chemistry confirms the conclusion: these rocks were formed in a wet world. Proving the existence of these rivers is the first and most critical step in the search for extraterrestrial life. Liquid water is a universal solvent. It breaks down materials to transport the essential nutrients that any biological system needs to survive. By flowing across the surface, these rivers acted as chemical mixers, creating the stable environments and energy gradients needed for simple microbial life to spark. NASA Mission Control now uses these geological maps to direct rovers on targeted investigations within these exact riverbeds. By following this evidence across every scale, we have isolated the most probable locations in our solar system to finally find our microscopic neighbors.